Hi, my name is Hamid Shojaei from Google. TPUs are Google's custom-developed ASICs used to accelerate machine learning applications. TPUs are designed from the ground up with the benefit of Google's deep experience and leadership in machine learning. A few years ago, we also developed and enabled Cloud TPUs. Cloud TPU enables you to run your machine learning workloads on TPU hardware using TensorFlow. It is designed for maximum performance and flexibility to help researchers, developers, and business owners to build their ML applications on TPUs. We also provided high-level TensorFlow APIs that help you to get models running on Cloud TPU. In our experience, models that previously took weeks to train on other hardware platforms can converge in a matter of few hours on TPUs. MLPerf benchmark results have been recently released, and here you can see that TPU demonstrated record-breaking performance at scale and can significantly outperform GPUs. Currently, all of our EDA workflow run on cloud. We started with using cloud for batch jobs in 2020. Then we moved our entire verification flow and finally switched to cloud for everything in 2021. That was a big win for us, because we have a perfect job management system on cloud, we have vast computing resources, there is a fast networking system, and we have lots of storage on cloud that could be used for our EDA applications. Some other benefits that we can get by moving to cloud is elasticity. So we are able to more quota in matter of few hours versus months for on-prem expansion. Another benefit is scalability. Solutions are designed with horizontal scaling. Here you can see how our total of daily job submissions to cloud has increased. We also get reliability by using cloud, because obviously you can eliminate a single failure zone with cloud capacity allocated across the entire globe. This was a super positive experience for us. We are collaborating with all EDA vendors to enable them on cloud. Now let's look at how our static sign-off methodology works on cloud. As soon as we have some RTL changes, we first run our pre-submit checks. I will provide more details for this step in the next slide. When the code is in, we kick off several tasks that run in parallel. We use RTL Linting tool for RTL Linting, autoformal, and CDC and RDC sign-off. We also elaborate RTL and report and fix issues regarding elaboration. The key advantage of this approach is that this process is early and continuous. Any changes in RTL will trigger the entire process again, and this approach will help us a lot in a static sign-off and makes it much easier to close. Imagine you want to wait for the entire RTL to get ready and verified before you do CDC verification. At that time, the CDC reports will be huge, and the noise number is too high and makes it much harder for you to close. Some more lights on our pre-submit step. This step is coming from the software world and has a huge impact on the quality of the code that we submit. In addition to code review, we have this feature to block committing a pending code change. Pre-submit checks include very simple, customizable built-in checks on the content or metadata of a change, such as naming conventions and readability standards. Thanks to the fast linting tool, we were also able to enable lint checks in pre-submit. As per our wish list, we hope we could run some CDC light checks in our pre-submit. For example, we can quickly check that there is no missing synchronizer in the design before the code goes in. Hopefully, EDA vendors can provide such features for us in the future. Two other enhancements that we applied to our CDC sign-off to support our complex designs were hierarchical run and multimode CDC. So our chips are huge, and it's not feasible to run CDC for the entire chip. At the same time, we don't want to miss any CDC issues at the top level. So what we do is that first we run CDC for every block, we clean all the failures, and then we use the tool to generate a database with the model for each block. Then instead of running CDC for actual chip top, we replace every block with the corresponding model, and this will make the CDC run at top level totally feasible. Another challenge that we faced was that due to the nature of our ASICs, we need to support SDC files that have multi-mode constraints. This means running the tool for different modes, reviewing of CDC issues in each mode separately, and several iterations to ensure that all modes are clean. And with the rapid rise in the number of modes in our projects, it is nearly impossible to sign off each mode individually. The solution is to use the CDC tool, which will have only one setup, one run, and one violation report. So we use this tool for CDC sign-off in the projects which have multi-mode SDC constraints. Another aspect is RDC. Our designs integrate a diverse set of peripherals, memories, networking, and I/O components that may come from different sources and different vendors. They can have different resets, power-up resets, and software resets, and sometimes they also have asynchronous resets. So in such designs, CDC is not the only reason for metastability. If the reset of the source register is different from the reset of the destination register, even if the path is in the same clock domain, this will create an asynchronous crossing path. This is called reset domain crossing, or RDC, and can cause metastability issue. Interestingly, we had an RDC issue in one of our projects because we assumed all vendor IPs have synchronous resets. After that, we started to use the RDC tool, again in a hierarchical mode. And this tool will make sure designers follow simple reset design rules to avoid metastability issues. Okay, in terms of what we are doing to further improve our ASIC design methodologies, we are actively working to use machine learning to aid chip design flows. The goal here is to develop a scalable and general ML-driven framework with rapid evaluation and turnaround time to shorten the chip design cycle. For that, as I mentioned, we use infrastructure on Google Cloud Platform. By GCP, which is the Google Cloud Platform, we can leverage the compute power and different ML algorithms which are available in Google Cloud to efficiently apply unique optimizations at all stages of chip design. We have already applied to 4 different stages: verification, which is both static and dynamic, failure planning, architecture, and design space exploration. 2-pronged strategies have been considered: existing solutions on Google Cloud Platform, which includes Bayesian optimizations and reinforcement learning. In addition, we are also working on some dedicated and advanced research solutions, such as graph neural networks and language models. Please contact me if you are interested in knowing more details about these new techniques. We recently published some papers, and I can send you if you are interested. Thank you.